sorry, I keep getting interrupted. So let's try this one more time. Let's talk about this rational function, which I know has been something tough for us all year. It's something that's been battling and battling and battling. So I want to look at this in a slightly different way. I want you to think about barriers, okay? If you look at this, graphing this function and think like, what are my barriers and how do I interact with those barriers? That might give you a really clear sense of how to maybe graph this function. And so there's some barriers that are natural. And so if I look at like these x and y axes, these are natural barriers um, to the function itself. And so one question you're going to have to answer is how in the world does this interact with those barriers? Like how does this graph and these barriers kind of come together? There's another type of barrier that's kind of part of the problem itself, which are the asymptotes. And so like this guy right here, oops, let me do this. So like these first three steps are barriers that we're going to put into the problem because we know it can't cross certain places or the end behavior has to kind of be a certain way. And we're going to have to answer like where those are and how our graph interacts. And then we're going to have to look at how the graph interacts with the barriers that we started with, the x and y axis. And that's all we're really doing. So it's really, if you think about it, a four-step process. What are the horizontal and vertical asymptote barriers? How do they behave? How do they behave around the x and y axes that we started with? And so let's jump into it. So the very first step is going to be the vertical asymptotes and the holes, because those set our vertical barriers. They set vertical barriers because we always are concerned with what we cannot use in the bottom of a fraction, i.e. 0. And so these x values that we can't use that create these zeros are going to turn out to be the things that define these artificial vertical asymptotes. And so the way we'll decide that is by factoring first and see if anything cancels. Because we need to figure out what the factors are because those roots, which are zeros, tell us where we can and can't live with our function. So we have 4x squared plus 4x plus 24. And so if we factor the top of this, we'll see that we can take out an x, of course, leaving us x squared minus 16, which would leave us with x plus 4, x minus 4. Okay? On the bottom, we can take out a common factor of 4, which of course leaves us with x squared plus x plus 6. Now here you're used to now factoring the bottom and maybe crossing something out, but something weird happens here. We have a plus x plus 6. Well, factor to 6 would be 1, 6, and 2, 3. None of those can create a plus 1 while still remaining a positive 6. And so in this particular case, we actually have no vertical asymptotes, and also no holes. So this is weird, but what we're telling ourselves that there are no additional vertical barriers besides the y-axis. And so that part is actually done. So our graph at this point is still this graph. There's no additional barriers that we need to put in. There's no x values that we can't use, which also tells us that our domain is going to be infinity to infinity. Weird for this type of problem, but not impossible. So now let's move on to horizontal asymptotes or slant asymptotes. So if we look at our function in its full form again, I'm going to rewrite it, x cubed minus 16x over 4x squared plus 4x plus 24. We'll see right away that we're not going to have a vertical asymptote at 0, nor we're going to have one that's a ratio of our leading coefficients, because we can notice that the powers here, the degree, excuse me, of the leading coefficients, the bottom is actually smaller than the top. So the way we'll expose this asymptote is actually by doing full division. And so we're going to divide by 4x squared plus 4x plus 24. And we're going to divide into x cubed minus 16x. Now this is weird because it's unbalanced, but it's not unheard of. All we have to do is kind of work these numbers. Now we're probably going to end up with something a little bit weird, but not unusable. Let me go ahead and reduce this. Okay, so we're going to start with a basic question. We have this 4x squared, and we're trying to get an x cubed. So what do I multiply 4x cubed, x squared to get x cubed? Well, first I have to kill the 4. I'll do so with a fraction 1/4, because a fourth times 4 is, of course, 1. And then I'll add an x here because x squared times x is x cubed. And so multiplying it through my function here, my outer function, I'll end up with x cubed, of course. Then I'll end up with plus x squared because a fourth times 4 is 1, x times x is x squared. And a fourth x times 24, excuse me, will be plus 6x. Yeah, okay. And so what we want to do is go ahead and subtract this line. Now we got to be careful. We know the x cubes will cancel, but I don't have any x squares, so I'll just have minus x squares because a negative and a positive, of course, makes a negative. And then we have negative 16x minus 6 more x's, should that be minus 22x, right? Because 16, drop another 6, end up at 22. And now we just continue. So now we're dealing with 4x squared to get negative x squared, so it tells me it's going to be a minus. And again, I need to get rid of this 4, so it's going to be another fourth. So 4th times 4x squared will just be, of course, negative x squared, so it's negative a quarter. Negative 1/4 times 4x will just be minus x. And a 4th times 24, negative 4th, excuse me, should just be minus 6. Okay? So we're subtracting this again. The x squares, of course, will cancel. That was by design. So we have negative 22x, add an x, that will be minus 21x. Okay? Then we end up with plus 6. Now, it turns out not to matter here, because if we look at our remainder, if we put that over our divisor, the remainder no longer matters over a large course of x. So even though it wasn't a perfect factor, and we do have some remainder, the remainder in this case does not matter. And so this turns out to be our horizontal asymptotes. It's not horizontal in this case because it has an x, it's actually oblique, but 1/4 x minus a quarter is going to define our asymptote, which will in turn define our end behavior. And so let's go ahead and try to graph this the best we can. It doesn't have to be perfect here, guys. We're just going for kind of generalities anyway. And so let me tick this in. Okay, so 1/4 x, that's a minus a quarter. So minus a fourth should be, I don't know, about right there. Okay. And so now we're going to add 1 to a quarter, so we get 1 1/4, so we go up 1, and then we're going to go over 4 for our slope. It's about right there. And we do the same thing below, so down 1, and then over 1, 2, 3, 4 to about right there. Okay? And so although not perfect, this line will define our horizontal asymptote. In this case, it's a slant asymptote. Oh, that got away from me. Which would be y equals a quarter x minus a quarter. Okay. Now, remember, this is going to define most of their end behavior, but we still have to determine whether or not it can cross. Again, we created a barrier, and now we got to figure out how, if we can at all, cross that barrier. And so, to answer whether or not we can cross this barrier, we basically have to see if two things can be equal. We have to see if our slant asymptote can ever be the same as our function, because graphically, that's what equality means. They cross one another. And so this is going to be some tricky algebra, so hold on to your hats here. We got to figure out if 1/4 x minus a fourth can ever be the same as x cubed minus 16x over 4x squares plus 4x plus 24. Now, to help with the algebra a little bit, I need to combine the left-hand side first, simply because I don't want to deal with like these fractions while I'm trying to like cross multiply and stuff. And so 1/4 x minus a quarter is the same thing as saying I have x minus 1 over 4. Okay, so I'm just writing it as a single fraction instead of a split fraction. Okay, and this guy can just come along for the ride. So now what we're doing is cross multiplying. Now from this point forward, we should acknowledge one of two things is going to happen. Either we're going to get an x value or x values, which means we can cross in one or more places, or we're going to get some nonsense like 0 equals 3, which means we can never be equal in the first place, meaning they never cross. I don't know which ones are going to be, but let's go ahead and execute the algebra. So let's cross up this way first because it's easy. That'll be 4x cubed minus 16 times 4 x. So 6 times 4 is 4, 4, 5, 6 will be 64x. Now let's cross up going the other way, which would be crazy more difficult, but it's algebra we can do. Let's multiply with the x first. So it'll be 4x cubed plus 4x squares plus 24x. I'm multiplying with the x. Now I'm multiplying the negative 1. So it'll be minus 4x squares minus 4x minus 24. And so we can see right away some stuff is going to cancel for us. Like the 4x cubed and the 4x cubed will cancel. And we probably want to go ahead and move this 64x over to the right-hand side. And so now as a massive cleanup step, we have 0. Let's see, we have 64x, and we have 4x squares here. Oh, minus 4x squares here. That's good. So those are both gone. We end up with 64x minus 4x minus 24. Okay, and that's it. So 24. Oh wait, the 24s will cancel. I missed that. Sorry. And so we just have 4x minus, or 64x minus 4x. So that's going to be 0 equals 60x. Well, we can divide both signs by 60, and we'll determine that this can actually cross at x equals 0. Okay? So it doesn't cross anywhere else, but it does cross at x equals 0. which means our line will actually cross right here. Okay, so just below x equals 0, um, or just below, excuse me, the origin. Okay, and so we have no vertical asymptote with this problem, but we do have a horizontal slant. It does cross x equals 0, and so the last thing that we need to determine are x and y intercepts. So how does it cross like the natural barriers that we had from the beginning of the problem? And so we need to grab our original function here, which I had copied, so I'm just going to paste it. Okay. And so now we need to figure out like x-intercepts and y-intercepts. All right. And so this should be fairly quick because we're just kind of determining some values here. Now recall the x-intercepts when the y equals 0. So if we're looking at the x-intercepts, we do want the y to be 0. And so that's going to be 0 is equal to x cubed minus 16x. I'm disregarding the bottom because the bottom can't be 0 anyway. And so if the right-hand side is 0, then just the top has to be 0. Now we previously factored this, and we know this is going to be equal to x times the quantity x plus 4, x minus 4, which means that we actually have 3 x-intercepts. We have 1 at x equals 0, one at negative 4, and one at positive 4. So we can actually put those into our problem. Let's see, 1, 2, 3, 4. It's going to cross here. 1, 2, 3, 4. It's going to cross here. And to make the middle kind of really, really convoluted, we're actually going to cross right here too. Okay, and so we kind of predicted that in our previous step that we can cross the intercept of the axis here at 0. And so it's kind of crossing because they're very, very close. So we have a crossing of our asymptote and a crossing of our axes at the same place. Now this also tells me that y will probably also be 0, but we can confirm that by looking at our y-intercept value. Remember, y-intercept value is when x equals 0, and so we have y to be 0 cubed minus 16 times 0 over 4 times 0 squared plus 4 times 0 plus 24. Now, everything here is 0, so the top is 0 over 24, which that means we cross at y equals 0, which we have already marked. So that's it. Like, we figured out where all the crossing points are. We have the slant asymptote, which we can only cross when it crosses 0, so it's going to be very close to the origin. And then we have these x-intercepts here that are going to cross left and right. Other than that, there are no other crossings, and so we should get a good sense of what our graph's going to behave like, because we know after this small window is going to tend towards the slant asymptote. Now, if we want to back that up, what we can actually create is what we call the info wave. Now, the info wave was just a way to kind of visualize the positive and negative regions of our graph. So we have 3 points in our info wave. We have a negative 4 x-intercept, we have a 0 x-intercept, and we have a 4 x-intercept. Now, rational functions by default always end positive. And so if you think about like the most parent rational function we have, which is 1 over x, 1 over x graphs like this, where we have a positive to the right of the axis, a negative to the right of the axis, and these are hard asymptotes, meaning that they can't be crossed. So the important thing to note here is the function always ends above the axis, which means our graph will end up above here too. Now, both the x-intercepts are multiplicity 1, so they're just going to cross through each time. Now, it's important to note this is not the shape of the graph, but what this will tell us is that from this point forward, so from 4 and larger, the graph is going to be positive. From 0 to negative 4, the graph is going to be negative. It's going to be positive again between negative 4 and 0. And the graph again will be negative from infinity all the way to negative 4. Okay, and so what we create up here has to mimic that. And so if we look at our first region, let me cut and paste this so it's a little bit higher for us, so we don't have to keep switching back and forth. Okay, so what this tells us, let me grab maybe green. Yeah, let's grab green. So what this tells us is that from our farthest right x-intercept to the right, we're going to be above the axis. And since we have the slant asymptote, we also know we have to get pretty close to asymptote without crossing it. Okay, so that's going to be that region right there. Okay, after the asymptote until the x equals 0, we got to be negative, but we do have to cross at 0, which means that we got to be below the axis, and then we have to come back up and cross at 0.
Oh, my bad.
It's that guy right there. So region 3, we're going to be completely above the axis until the intercept. Okay, and I just graph that picture right there. And then after that, we're going to be completely negative, but then we're going to have to hug this y-intercept again. I'm sorry, slant asymptote again. And so that should be a pretty accurate picture of our graph. Now, yeah, the behavior here is going to be a little bit hard to see because I have to hit 0 and then immediately cross the axis kind of at the same time. So it's probably a little more dramatic there, but it gives you a pretty nice picture of what we're looking for. And so that's what we are looking for at the graph. Now, as far as the end behavior, okay, the end behavior describes what's happening extreme left, extreme right. So as this green line tends towards the red dashed line, we can examine the limit as x goes to negative infinity. Now this is going to do what the red line is doing, and the red line is consistently going down, and so this actually is going to tend to negative infinity. We can do the same thing here for that green line. The limit as x goes far to the right is going to tend toward the red dashed line is going to do. And that red dashed line, since it's linear, will consistently increase, so it goes to infinity. Guys, this is a massive, monster problem. This one's weirder than most of them because we had no vertical asymptotes. But again, like you break it up into small steps, like it's really not as bad as it seems. First, we check about vertical barriers. In this case, we had none. But if we had some stuff that we could not use to make 0 in the x-axis, I'm sorry, the bottom of the x values to the bottom of the fraction, those would have turned into asymptotes. The second thing we do is check for the horizontal or slant ones. These describe end behavior, of course, but in this case we had like a line because it was a slant asymptote, but these are barriers we're putting in. Then we have to test whether or not we can cross those barriers, which tends to be a very messy algebra problem, but totally doable if you're careful and just show all your work. The last step is we have to figure out how our line crosses the barriers we started with, in other words, the x and y intercepts. And we just use a very simple definition: x intercepts when y is 0, y-intercept is when x is 0. An optional thing to help us understand if we're above or below the axis is our infrawave. We take advantage of known end behavior for a rational function, and also what we know about how the line will pass through roots of like 1 power. That's the infrawave. Okay, so in the end, we get this kind of crazy thing. Now, if you graph this in a graphing calculator Desmos, you should see pretty much an exact copy of this, but much more precise than what I'm offering here. But guys, that's it. You're going to see 4 more of these or 3 more of these over the next couple homeworks. So make sure that you're keeping caught up. Okay. So we do have a test coming up next Thursday. So that's only like 4 blocks away. So make sure you're keeping up on your homework so you can totally take that test and have a really, really great spring break. Okay, guys, that's it. Thank you for listening. Goodbye.